Question 16 says, how many of the following molecules are polar? So in order to find if they're polar or not, we need to draw the Lewis structures. In this question, I'm going to draw all of the Lewis structures. In the previous questions, or the subsequent questions, I'm going to refer you back to this question for how to draw the Lewis structures, or to refer you back to the lecture notes where we go through how to draw Lewis structures. But drawing the Lewis structures is essentially a four-step process that starts by counting the valence electrons, which is equal to the A group number. So if we look, both chlorine and bromine are in 7A, so we each have 7 valence electrons. So we have 7 plus 3 times 7, which is a total of 28 electrons for BrCl3. Okay, and so basically we have 4 total atoms, each one has 7, so 28 electrons. We're going to put bromine in the middle, and we're going to bond it to 3 Cl's, like so. Okay, so we put the least electronegative atom in the middle. Remember, fluorine is the most electronegative, and as we go down, as we go up and towards fluorine, they become more and more electronegative. So chlorine is closer to fluorine, so it's more electronegative, and bromine is further from fluorine, so it's less electronegative. So we put the least electronegative atom in the middle, step 2, which is bromine. Now we want to fill the octets. So if you count by 8, it can be very helpful. If I put 8 electrons, or put an octet around each of the chlorines, okay, 3 eighths are 24. So now I've placed 24 of my 28 electrons. Now I have to decide where to put the other 4 electrons. Well, the first thing is I haven't filled the octet on bromine, so I'm going to put one of the 2 electrons pairs on bromine. So now I have 2 more electrons that I have to place. I can expand the octet of both chlorine and bromine, but I'm going to guess here that bromine doesn't have enough electrons, so I'm going to expand the octet of bromine to use those extra electrons. Remember that if atoms are period 3 or lower on the periodic table, period 3, 4, 5, 6, 7, you can expand their octets. So I can expand chlorine and bromine, but I'm going to expand bromine because chlorine had more electrons around it. Now I want to count the formal charges. And a formal charge is essentially comparing the number of electrons around the atom to the number of electrons that it wants to have. Specifically, I want to count the dots as 1 and count the dashes as 1, because in this dash there are 2 electrons, but one formally belongs to bromine and one formally belongs to chlorine. So in formal charge, I'm going to count this as 1. For the lone pair electrons, which always come in pairs of course, I'm going to count them as 1 each. So 1, 2, 3, 4, 5, 6, 7. Dots is 1, dashes is 1. Chlorine wants 7 because it's in 7A, has 7, it's neutral. This chlorine's the same, this chlorine's the same. Now for bromine, I want to do the same thing. It wants to have 7 and has 1, 2, 3, 4, 5, 6, 7. It is also neutral. So this is a good Lewis structure. Now I have to decide if it's polar or not. Well, I want to look at bromine and I want to decide are all domains the same. Well, no, they're not. 3 domains are chlorine and 2 domains are lone pairs. So of its 5 domains, they're not all the same. That makes this polar. Let's look at the next one, CS2. So for CS2, I want to draw or count the valence electrons. That's the first step. Carbon's in 4, so it has 4, 4A, so it has 4, plus 2 times 6, sulfur's in 6A, which is a total of 16 electrons. Put the least electronegative atom in the middle. Carbon is farther away from fluorine than is sulfur, so carbon goes in the middle, and we bond it to 2 sulfurs because it's CS2. Now, I want to place my octets by using the 16 electrons. Well, 2 eighths are 16. So if I put 8 electrons around each sulfur, 8, 2, 4, 6, 8, 2, 4, 6, 8, 8 total electrons around sulfur, so 2 eighths are 16. I've used all the electrons. But I haven't finished job 3 yet because I have not filled the octet of carbon. So if I don't have enough electrons, I want to use rule 3a, which is to make multiple bonds. So I'm going to move these like this because I need to give carbon some more electrons. And what I end up with is this, which looks an awful lot like CO2, but this is CS2. Okay, so Now I want to calculate the formal charges. Sulfur wants 6, has 1, 2, 3, 4, 5, 6. It's neutral. Carbon wants 4, has 1, 2, 3, 4. It's neutral. This sulfur and the sulfur are the same, so they're all neutral. Now I want to decide if it's polar or nonpolar. Carbon, the central atom, has 2 domains, but they're both the same. Since all domains are the same, this one is nonpolar. In this case, both domains are sulfur. Let's look at the next one, SiF4. So, silicon is just below carbon, so it has 4 valence electrons, plus 4 times 7. There's 4 fluorines in 7A, so that is 32 total electrons. Put the least electronegative atom in the middle. Fluorine is the most electronegative atom, so it definitely doesn't go in the middle. So I put Si in the middle, and I bond it to 4 fluorines. 4 eighths are 32. So I'm going to fill the octets of all of the fluorines, and just by coincidence, this actually fills the octets of everything and completes rule of 3. So now I want to determine the formal charge. Fluorine wants to have 7 electrons around it. It has 1, 2, 3, 4, 5, 6, 7. It's neutral. All the other fluorines are the same. Silicon wants to have 4 electrons around it. It has 1, 2, 3, 4. It's neutral, so all formal charges are 0. This is a good Lewis structure. Now what I want to do is determine if it's polar or nonpolar. Silicon has 1, 2, 3, 4 domains, which are all fluorine. All domains are the same. This is nonpolar. Finally, SO3. So SO3 is a tough one. So sulfur is 6, and oxygen is also 6. So it's 6 plus 3 times 6. 24 total electrons. I put sulfur in the middle, and I bond it to 3 oxygens, like so. Now I realize that if I put 8 electrons around each oxygen, the 2 in the bond plus 3 lone pairs, that will fill the octets of each of the oxygen atoms. Okay, but I have not filled the octet of sulfur. So, rule 3a, I don't have enough electrons, so I want to move those in, and I get sulfur double bonded to an oxygen, like so, single bonded to an oxygen, like so, single bonded to an oxygen, like so. Okay, now I want to determine whether or not this molecule is the best Lewis structure, and to do that I want to do formal charges. Now I have 2 different types of oxygen. So I have the double bonded oxygen, which has 1, 2, 3, 4, 5, 6. Oxygen wants 6, has 6, it's neutral. I also have the 2 single bonded oxygens, which want 6 and have 1, 2, 3, 4, 5, 6, 7. This has an extra electron, and it's minus. This one's the same, so it's also minus. The sulfur wants 6 and has 1, 2, 3, 4. So it's missing 2 electrons, and it's 2 plus. Remember that the last rule is not to just calculate the formal charges, it's to minimize the formal charges. And this has an awful lot of formal charges. So what I want to do is, I want to see where sulfur is on my periodic table. And sulfur is in period 3, which means it can expand its octet. So if I move these 2 electrons and those 2 electrons into more double bonds, I get sulfur double bonded to all 3 oxygens. And what this does is it puts 2 more electrons around sulfur, because remember, formally 1 belongs to sulfur, 1 belongs to oxygen. So by making 2 more double bonds, I've effectively put 2 more electrons around sulfur. I've also effectively taken 1 electron away from each of these oxygens, because I made it from a lone pair into a bonding pair, so formally only 1 belongs to the oxygen. Said another way, this molecule has no formal charges. Now I want to calculate the domains. I have 1, 2, 3 domains, and they're all oxygen. This is non-polar. Note that even if you had just drawn this one, you'd also get nonpolar, because this has 1, 2, 3 oxygen domains, and it's also non-polar. This is wrong, but but if this did exist, it would have resonance and would truly be nonpolar. You do not consider a single bonded oxygen and a double bonded oxygen as different domains. Why? Because of resonance. So either one you used, you get nonpolar. So finally it asks how many of the following molecules are polar. Well, we found that only one of these 4 molecules is polar. Now I'm not going to spend this much time drawing the Lewis structures that are going to be needed moving forward. I'll just kind of draw them. So please refer back to the video on drawing Lewis structures, because these are just not good examples to start with. All right, these are good examples to do after you've practiced a bunch of other examples. And in that video, I start with a more simplistic example like F2, and that's going to be kind of building up the idea of how to do this, which is very important, as opposed to just doing these more complex examples on a test, practice test.